All right, while we work on getting these started, I'm just going to write a couple things up about general logistics and continue to work on this for a second. All right. Okay, great. Well, why don't we dive into this? Let's see. So I think everybody agreed from the first one, which is great. So this is true. So this is true. There was a bit of disagreement about this B and C. So why don't you talk to your neighbor for a second and see if that changes your mind or resolves the confusion.
I thought behavior coding uses demonstrations, but dagger is like it's easy to yes, that was correct. Because one of the downsides is we need constantly evaluation. And I think that's what I thought, where dagger is needed a little bit more than just demonstrate. Because it's able to quick trajectory, but then oh, that's a good thing. Whereas behavior coding, I mean, just require the diagrams, just general. But we need some type of leading sense.
All right. So the first one is, this is false, and this is false. So Dagger, if you think back, unfortunately required the human to keep around forever. They would constantly be getting asked, hey, for the policy that the agent followed, was this an optimal action or not? And behavior cloning does not require knowing the dynamics model. It allows us to reduce reinforcement learning to supervised learning. And the idea is that we take the expert demonstrations and we just try to learn state to action mappings. And so we can just treat it as a standard supervised learning problem. Great. All right, so I think, as we go further in the course, we get to go to more and more exciting topics. And today we're really going to start to see how, skipping all the NLP side, but how do we actually get to reinforcement learning that can do some of the amazing things that we see large language models doing. So for example, when I was preparing this lecture, I was like, please write me a program to demonstrate how RLHF works, be brief in your explanations, and then show me the code. And within about 5 seconds, it generated me code that used Q-learning and other things to generate an actual example of how RLHF, which stands for Reinforcement Learning from Human Feedback, which is how they trained ChatGPT, amongst a whole bunch of other things to do. So it could generate me a small example of how to do that in code that you can run. So that's pretty extraordinary. This was not possible, 2 years ago. Well, I started offering this class in 2017. So when I first started offering this class, this was definitely not possible. And this only really became possible with ChatGPT. So it's pretty phenomenal that we now have AI that can do this. And the question is, how do we get there? And what sort of RL techniques are being used to help accomplish this? So that's what we're going to start digging into now. So today what we're going to do is we are going to continue on from imitation learning and talk a bit about reinforcement learning from human feedback. And then next time, we're going to have a guest lecture from one of the authors of the direct preference optimization work, which received Best Paper runner-up at Neural Information Processing Systems, which is kind of the premier machine learning conference. So he's going to come talk. He's one of the graduate students here at Stanford. And this is sort of have become, really, I guess maybe like it's starting to replace or exceed performance on RLHF on a lot of benchmarks. that's super exciting. It'll be great to have him. And in fact, because everybody here always is innovating, which is awesome, he was like, oh, well, we actually have a new paper coming out in arXiv like next week that shows how we can extend this in all these different ways. So I asked him if he had time to cover that a little bit. So there's a lot of work to be done in this space to think about how do we better use RL in combination with these incredible function approximators of large language models to create, sort of the amazing performance that we could see of a system that could do something like this. So that's where we're going. What we're going to focus on today is to continue talking about imitation learning. And I think imitation learning is a nice way to build into this because imitation learning is one form of using human feedback to try to train reinforcement learning agents. And then when we get into RLHF, well, that'll be sort of a different way to leverage human expertise. So to start, we're going to go back to imitation learning and to talk a lot today about max entropy inverse reinforcement learning. So let's just remember where we were last time. What we were talking about when we talked about imitation learning was the idea of taking demonstrations from people. And these either could be explicit demonstrations, like I show the robot how to pick up a cup and it records all my movements, and then you can use that for later training. Or it could just be natural trajectories. So like you take electronic medical record systems and you just look at the decisions that are made from doctors. And we use that to try to either equal doctor performance or exceed doctor performance. So often we just have observation data, which may either just be done in normal sort of business as usual, or that is explicitly being given as a demonstration trajectory. And this is just going to be the sequence of states and actions. We're not going to have rewards in general. And so the idea was, well, it might be easier in some cases, either because it's just sort of natural data traces that are being generated as they're part of their normal work, like electronic medical record systems are, or because it's hard for people to write down a reward function that kind of captures all the complexity of what they're trying to do in their objective. So that was one of the motivations for this. And we saw a few different ways to try to think about this setting last time, including behavior cloning, where we just map things back to supervised learning, and we try to learn a policy directly to match the expert. We saw Dagger. I'll put that on here too. So another thing that we saw kind of in between these two was Dagger, which tried to address a challenge of behavior cloning, which is that when you make mistakes in your supervised learning system, you may end up in parts of the state and action distribution that you don't have good coverage. So we talked about this kind of race car track example, where like once you go off, you've got a distribution mismatch. And we'll hear more about distribution mismatches in RL later in the course. And there we wouldn't necessarily know what to do. And so what Dagger said is we have to keep an expert around, and then they will always tell us what you should have done. So they kind of a coach go back, they replay, how you did in that hockey game, what you should have done at each moment. And there's a lot of really interesting questions of kind of thinking about those counterfactuals. And then we thought about this broad question of, well, could we recover the reward from looking at these demonstrations? And this could be useful within its own right to try to understand the objectives that people are using when they're making their decisions for different areas, as well as potentially for learning a better policy or learning the policy. And then can we also sort of, once we have that R, generate a good policy or generate a good policy directly? So one of the ideas that we talked about in this case is, well, what is sufficient to be able to accomplish mimicking? So in particular, we said, well, if we want to get a policy that matches the expert, that is equivalent to generating trajectories where that distribution over those trajectories is the same as what the expert would have done. So we kind of think of this strong relationship between policies to trajectories, which also is to states and actions. Because we can think of there being a policy that induces a distribution over states and actions, and two policies that induce the same distribution over states and actions will have the same reward. Because we're assuming that the rewards are only a function of the states and actions. And so we talked about how people had sort of leveraged this assumption to think about different ways to try to learn reward features. So for example, if you have a set of features determined by your policy, so this might be mu, which could be things like, how quickly a call service agent responds to calls, how many times they use positive sentiment, things like that. And of course, in the case of a robot, it might be how many times it hit a wall, how far it went, any of these sorts of features. You could imagine that your reward function is just a linear combination of those features. And so we saw.
So these features are just things that people can come up with for every problem?
Great question. So I would ask, are these features like people are writing down per problem? Historically, yes. I think one of the big things with deep learning has been like, let's at least go as close to the sensors as possible. So can we use like just images instead of features on images? But in the case of something like, say, online marketing, a lot of them would be potentially predefined. So, purchases and what web pages you looked at and what things search queries you did. So you would have to still enumerate a set of features in this case that you're defining your reward over. But ideally, it's sort of as close to the sensor level of the data you're collecting as possible. Or at least that often has a big advantage. So what we saw here is that essentially, because we assume if things are linear, and we assume there's just like this unknown weight vector, so this is a vector, this is a vector, we could say if you could make sure that your distribution over features is really close, and if you bound the norm of the weight vector, then being really close in features is the same as being really close in reward, which means if your policy can induce the same features, you can get the same reward. This is a recap from last time, but it's useful to think about as we go forward. So one of the big challenges we talked about last time is that there is not a unique reward function that is compatible with the observed data, even if you assume your observed data is optimal. So we talked about how even the zero reward is compatible with any policy you might see. And so in general, it's not going to be identifiable. We can't just like say, oh, if we observe these trajectories and we know the policy is optimal, this is what the reward is. There's too many rewards that are compatible. And so what we're going to spend a lot of time on now is to think about one choice for how to kind of break that ambiguity. Okay, and this is where we left off last time. And what we're going to focus on now is maximum entropy IRL. Gale is also, the second one is known as Gale. This is also a popular approach. This was developed by Stefano Orman's group here at Stanford. But we're going to start with max entropy because also there's a lot of other follow-up things that could be useful from this idea. Okay. So we're going to talk about max entropy inverse RL. This came out in 2008. And it goes first with the principle of maximum entropy. Raise your hand if you've heard of this before in the context of probability distributions. Okay, a few people, more than I would have expected. Cool. All right, so remember that the entropy of a distribution P, so think of, this is a probability distribution. So remember we've got this. This is something, so we'd have like sum over all S. If you have a discrete state space, this is just a probability distribution. So the entropy of a probability distribution is minus the sum over all of the states, the probability of that state times log of the probability of the state. It helps capture sort of, how distributed our distribution is. And what the principle of max entropy says is that the probability distribution, which best represents the current state of knowledge. What do we mean by current state of knowledge? Is sort of, if we have some previous data, the one that we should pick is the probability distribution we should write down is the one with the largest entropy given the constraints of the precisely stated prior data. So you can imagine you have your expert data, and what this says is that, and we haven't talked about what these probability distributions will be yet, but what this says is that we're going to try to write down distributions over your we're going to look at trajectories in particular, that are compatible with our observed trajectories, but otherwise have the highest entropy. And so intuitively, you could think of sort of, if you have some data, you want to find probability distributions that are consistent with that, but have the highest entropy on, given that they're consistent. So we're going to end up with something where you have constraints. Yeah?
I don't understand the motivation behind imitation to learn. Are we trying to not deploy the export model because it's expensive? Are we trying to distill the model size? Like, what's the...
What are we trying to do with imitation learning? Or?
Yeah, what's the motivation for doing this? Because we already have access to an expert model, right? Why learn another model?
Well, the idea is that you have access to trajectories over the from the expert. So you don't have access to the expert at all point. You don't have their policy. You just have observations. So you can imagine something like, if I'm an expert doctor, you could look at all of the ways that I do surgery, and you could like look at all of my movements and stuff. And then what I want to do is have a robot that can imitate that. And so I need to distill it and make it sort of, into an explicit parameterized policy. Is that?
Yeah.
Yeah. Okay, cool. All right, so this is an interesting idea. This is sort of saying this is one way to break ties. Like there's a whole bunch of different reward functions, a whole bunch of different ways you could maybe be compatible with the observed data. Let's pick ones which have the maximum entropy. Okay, so this is just a choice you can make.
What does it mean for a probability distribution to be consistent with the observed?
Great question. Okay, so hold on to that for a second. I'm going to say, yeah, so our question is, what does this mean? Like, how do we actually make this mathematically formal and algorithmic? And we'll see that in like the next slides. That's a good question. We're going to write this down in a formal way. Okay, but this is the principle, and so this is what Brian Siebert and his colleagues thought about in terms of this method. Okay, and I'll just say a little bit about the motivation. So Brian was a grad student at the time at Carnegie Mellon, and they were interested in trying to understand taxi driver behavior. And so what they wanted to do is, when you're driving, there's lots of different constraints, particularly if you're a taxi driver, you want to think about distance and potential traffic and, tolls and all these things. And so what they wanted to do is just to take trajectories of people driving through the streets of Pittsburgh and then try to infer what the reward function was that taxi drivers were using, as well as be able to have a policy that did as well as like good taxi drivers. So this was sort of part of the motivation, and they had to deal with this question of how do you can't just learn a unique reward, so like, let's just try to find something that's got maximum entropy. And let's see what this means in this case. All right, so in the linear reward case, what we're going to be interested in, or how we're going to think about where max entropy applies, is to say, we're going to have distributions over trajectories. So we're going to have distributions over trajectories, and we want to find a distribution over trajectories that matches our observed distribution over trajectories from the expert, but otherwise has really high entropy. So what you could be learning in this case is a probability distribution over trajectories that has the maximum entropy, subject to the fact that it is a true probability distribution. So that's one constraint. So this is just subject to. You either think of subject to or such that, but the other ones are constraints. And the other is that in this case, we're going to say we're going to want to match the features. And we saw before that matching the features was equivalent to being able to match the rewards in the case where you have a linear function. So in the linear reward case, what we want to do is we want to say, I've got my distribution of trajectories. Let's say mu is a function that just takes a trajectory and outputs a set of features. And we'll talk about some other choices for that soon. And we just want that to match what the features were we observed from the trajectories from D, where D is a data set from our experts. Okay. This is like from our experts. Okay, so this is how we would write that down. Now, I haven't told you yet how we're going to learn the reward function. I haven't even told you how we're going to learn this, but this is where the maximum entropy assumption is being applied. It's saying what we mean by maximum entropy is we want to think about getting a distribution over trajectories that is compatible with our expert data, but otherwise has the maximum entropy. Yeah. Remind me your name one more time. Yeah.
When you say distribution over trajectories, does that mean distribution over policies that create that trajectory, or is that something else?
Great question. That's sort of isomorphic. So you can just think of it directly as being, distributions over state reward, state action, et cetera. Or you can think of it as it's implicitly going through a policy that is generating those. Yeah. And we'll become clearer too about like sort of where the policies come in. Great question. Okay, so this is what this would say, but we haven't got into rewards yet. And we need to think about how do we go from this to thinking about learning reward model and learning policies. Okay. So in general, we don't have rewards, but if we did have rewards, what we would like to do is to get a policy that induces trajectories that match the same reward as our expert. Okay, so we would like to, get a policy that has as high reward as our expert. If we knew what those were, like if we had a way like this R phi, then we would say we want our distribution. So let's say we're going to learn a distribution over trajectories. We want this to be the same as what the expert is. And I'll just highlight that here I'm using this p hat for expert. Okay. All right, so this is expert. Okay, so this looks almost the same as above, except for I've said, well, let's imagine that we don't necessarily have to have a linear reward function. In general, we just want to say we would really like that whatever our distribution of trajectories is that it matches the reward of the experts. Because we know the experts is optimal, so if we achieve this, we're good. Okay, so we would like to be able to solve this problem. We don't know what R is still, so we can't do this, but we're just going to look at what would be the solution to this problem. So, and where we're going to go from this is that we're ultimately going to end up with an algorithm that does something like the following. We are going to assume we have a reward function or compute one. Once we have a reward function, we're going to learn an optimal policy. And then we're going to update our state or trajectory features to update our reward function. And we're going to do this many times. So we're going to be thinking really a lot about the relationship between reward functions to optimal policies to distributions over states and actions, distributions over states and actions to how can we update our reward function. Okay, and we're going to step through all of those steps. Okay, and in the original paper, they assumed the dynamics reward model is known. All right, so let's step through the first part, because I think it's really helpful to see often when people talk about max entropy, then they introduce this sort of exponential family, and it may or may not be clear where that comes from. Okay, so remember that we have this constrained objective. So we have this thing here. Okay. All right. So what we would like to understand in this case is, given a constrained objective, if we knew the costs, what would be the form of the distribution over tau? Okay, because remember what we've got here is we have a max. So what this thing is this is an objective. This is an optimization problem that says the right distribution over trajectories you want is the one that maximizes that expression there. And what we're going to do now is we're going to see what would it be like if we knew all of those things, what would the sort of structural form look like? Okay, and then we're going to use that to make some other steps. Okay, so now this is just to get intuition over this functional form. What we're going to do is we're going to rewrite this as using Lagrange multipliers. Okay, so we've got p here. We're going to introduce lambda. Okay, and I'm just going to write this as follows. Lambda sum over tau. And I think this is illustrative because it'll make it really clear where these sort of structural forms come in that we're going to use. Okay. All right, so I'm just writing down our first Lagrange multiplier, and I suspect most of you have seen this, but if you haven't, feel free to come up to me afterwards. Okay, we're just rewriting the constrained optimization problem. Okay, so we rewrote our constrained optimization problem as a single equation, and now we're going to take the derivative with respect to this. Okay, because remember we want to optimize this. So we're going to do d. We're going to do it with respect to our trajectories. And so we're just going to get log of p of tau plus p of tau times the derivative of log, which is just 1 over p of tau, plus okay, and in the third case, the third one doesn't have any p of tau, it just this term does here. So you'll get lambda 1 r phi of tau. Yeah.
Does the summation go away because we're only taking the derivative with respect to one specific trajectory?
Yeah. Exactly what I said. So we're going to assume we're trying to get what is the derivative with respect to one, like this probability, this particular trajectory tau. Okay. That's why everything goes away. And the important thing to notice here is this goes away because there's only a p hat there. It was from the expert. So that term just disappears. It's not a function of p of tau at all. Okay. All right, so now we want to set this equal to 0. We're going to set this to 0 because we want to find the max. And then we're going to just do some algebra. Okay. Now we're just going to exponentiate. Okay. Why did we do this? Because I wanted to illustrate that what this means is that the probability distribution over trajectories, which maximize the entropy subject to some constraints, is exactly proportional to, so this is the proportional side, the exponential of the reward for that trajectory. Okay. Which means that, in general, if you observe this, you would put sort of exponential more weight on things that have higher reward, subject to a constraint that you have a probability distribution. Okay. All right. So what this shows here, okay, is that if we want to take this principle of max entropy, then what we end up getting is that the functional form over our trajectories is this exponential. It's proportional to an exponential. Okay, and that's an exponential family, for those of you who've seen this before. I've seen exponential families. So this is like the structural form. This is the distribution that maximizes the entropy. And so once we know that, we can leverage that to now start to try to learn a reward function. Okay, so let's see how we do this. Because remember, we just did this assuming that R phi was known, like for a particular R phi. We're not taking a derivative with respect to phi here at all. It's just a derivative with respect to p of tau. Okay, all right. So what this means is that we can think of maximizing the entropy over the probability distribution with respect to tau is equal to maximizing the likelihood of the observed data under this particular max entropy distribution. Okay. So I'm going to just write out what that would be here. So remember, that's what we saw here. We saw that if we max entropy, the functional form we get looks like this normalized exponential. Okay. So in particular, we'll just write that out again here. Okay, so what we get is we say the probability of a particular trajectory tau I, given some reward model phi, is equal to 1 over z of phi, and I'll define that in just a second, e r phi tau I, okay, where z of phi is our normalizing constant, because we have to have a well-formed probability distribution. Okay, so let's say this is structurally like what it looks like. And notice that we can also write this in terms of states. Okay, so this is also equal to e to the sum over all the states inside of your trajectory. Okay. Where I'm sort of abusing notation a little bit to both use r phi of tau or r phi of state just to mean the reward you get from a particular state or the reward you get from a whole trajectory. So notice we can use each of these, and this is our thing. So why is this helpful? Okay, so we don't know what the reward function is. We don't actually have that, right? Yes? But what this means is that since we know what the functional form is of the probability of tau under the max entropy principle, we can now say, okay, I'm not going to worry about this part. I'm going to assume this is the structural form. Now my unknown is just phi. And now I'm going to try to maximize the likelihood of my observed data by changing the parameterization of phi. Okay. So this observation, and when I say this observation, I mean that the probability over tau that maximizes entropy, constrained entropy, looks like a normalized exponential, means we can now estimate or learn R phi by maximizing the probability of our observed data. So we're going to treat this as a maximum likelihood problem. Okay. All right. And I'll just note here, this is a really elegant observation. This came all the way back from Jaynes in 1957. So when people were thinking about what does it mean to maximize the entropy of something subject to some constraints, they realized that you could convert it to this exponential family. And then once you have that, now you have something where your uncertainty is only with respect to this phi. And in fact, this type of insight at a very high level will be related to what you'll see next week in terms of direct preference optimization, where sometimes we might be able to reparameterize our objective function to be able to get rid of, you might call them almost nuisance parameters, things that you might not care about directly, where you have sort of one parameter you really want to learn. Okay, so let's see how we can do the maximum likelihood. So now what we're going to try to do is we're going to try to actually learn that reward function. And we're going to leverage the fact that we know the structural form of this probability distribution over the trajectories. So what we're going to do is we're going to say we're going to maximize phi of log the probability over all of our data. So this is our expert. Of the probability of each of those trajectories. So we're just saying we're going to try to maximize the probability that we observed the data that we did under our reward function. Okay. And because of our structural form, we can rewrite this as follows. This is going to be a sum. So I'm just going to say log of product is the same as sum over the logs. Then I'm going to plug in what my form told me that my probability distribution has to look like for my trajectories. Okay. All right. So this is just me plugging in that sort of max entropy form of the trajectories. And now I'm just going to split that apart. So I'm going to rewrite it. The log and the exponential cancel. And then I have log of the normalizing term. Okay. Now, notice that in terms of this part, so notice that this is independent of tau star. Okay, so this is, independent of all those. We end up with two things. We have max over phi, sum over tau star, in our data set of R minus the size of our data set times log sum over tau. Okay. And the reason that happened there is this was all inside the sum. This was completely independent of tau star, so I could bring it out. The number of trajectories that I have in D is just the cardinality of D. Excuse me. All right. So now what we can do is take a derivative. Okay. So I'm gonna call this whole thing J of phi, because it's all parameterized by my particular reward function. I'm going to take the derivative of that, because in general we're going to do everything with gradient descent, as usual. Okay, so this is going to look like the sum for all my trajectories in my expert data set, the derivative with respect to my reward function, minus, let me see if I can make this nice and big for this part. Okay. Okay, so we're going to have two things. We have this log, so we're going to have to take the derivative of that. This goes on the bottom. Okay, and we're going to play a small We're going to observe something in just a second, okay? So then we're going to still have our sum over tau, e to the r 5 tau times the derivative. So I'm just taking the derivative of that whole term. Okay. All right. The important thing to notice here, so I just took the derivative of both of these parts. This thing should look a little bit familiar, okay? This is in fact just the exact expression we got for what is the probability of a particular trajectory. Okay, let me just put that in. Okay, so note, this is just equal to the probability of tau. Given phi, let me make sure I put given phi. All right, because that's just this normalized exponential divided by that. So we're going to have this. When you put that, I shall be careful. Let me just make sure I write that carefully. So this is going to go to this because this is equal to e to the r phi of tau divided by the normalizing constant. Okay. So we can move this. We can move this outside part into here, and then that expression in there, which is this, is just equal to probability of tau given phi. Okay. All right. So this. Go back to here. Okay, so we just end up with the following. We get the derivative with respect to the reward function for every trajectory inside of our expert data, minus the number of different trajectories we have, times the sum over all trajectories, the probability of that trajectory given phi, times the derivative with respect to phi at that point. Okay. And that's our gradient step. So what this would say here is if you want to take a step towards optimizing, then what we would do in this case is you could compute the derivative with respect to your reward function. Okay. All right, we have a few more steps to go. So the next is, this is all in terms of trajectories. We'd like to get in terms of states. So for that, we can just observe the fact that, as before, the probability of trajectory can be broken down into its components. Okay. So this is just equal to t equals 1 to the length of your trajectory, the probability of your A given S. This is like your policy. And the probability of ST plus 1 given ST and AT. Okay, this is just the probability of a trajectory, and we've seen this before. If we have that the probability of a trajectory is proportional, as we've seen, to e to the minus r phi of a trajectory, and we know that we can write that also as equal to e to the minus sum over s inside the trajectory of r phi of that state. So then we can think of plugging that in for our derivative, and what we get is the following. So it's just the same derivative now, but in terms of states instead of trajectories. So this is for all the states inside of your expert demonstrations. You take the derivative with respect to that state, minus d, sum over the states, probability of the state given that in the trajectory, and then the derivative with respect to that state. Okay. And why is this interesting? This is interesting because basically what we're getting in this case is we're getting stuff that looks like us trying to match the distribution over states that we see in the data set. Now, when we think of doing this, one other thing to note is, where do these sort of state densities come from? So essentially you could think of it as, I have some observed states and actions, and I'm going to think about under a different policy what states and actions that will induce. If you know the dynamics model, and if it's tabular, so if tabular, so if you think back for a few weeks ago, tabular, and the dynamics are known, then you can actually compute the state action distribution directly using dynamic programming. Okay, so, and pi is given then you can actually just directly compute the states and actions. So let's see that. So you could say mu1 of s is equal to p of ss. And then for t equals 1 dot 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 t, so this is time indexed. Okay, so this is like, again, remember at a high level what we're trying to do here is we're learning that we are getting, we're trying to match the state action frequencies between our observed policy from our experts and what we induce under our reward function. What this is going to say is that you're going to try to estimate a reward function, you're going to try to compute an optimal policy given that reward function, and then you're going to try to count and see what your state action distribution looks like under that resulting policy. If it matches your experts, you're done. Otherwise, you need to keep changing your reward function, your policy, and the resulting state action distribution until they match. Okay. All right, so I'm just going to go through briefly so you can see how this is computable. All right, so what this would say is that your distribution of states on the next time step depends on your distribution of states on the previous time step, the probability under your policy. So this is your policy. Actually, I'll be a little careful there. The probability of the action given the state and the probability of the state given the state in action. And you can use this then to sum up over all time steps what your sort of average density is for a particular state. Okay. So what this means is that when you're trying to actually compute the derivative of your objective function with respect to the reward, then what you end up getting is that you can plug these in, and if you have, so you can write down this, I'm going to get so you can see that it's fairly involved, but it is definitely possible. Sum over all your states, probability of the states given by t, and your reward function. And this will simplify a bit if you have, so let me just write out, if your r is equal to just this times some features, then when you take the derivative with respect to the phi, you just get the features. Okay, so this would mean that dr phi of s, so if linear, just equal to your features. Okay, so I know this is a lot of algebra, but what this is saying is that your derivative about how you want to change your reward will just end up being a sum over all the features you have inside of your data, minus this additional term. Okay, so you sort of compute all of this with respect to your observed features and the features you have in your data set. All right, so how does this all work when we put this fully together? What we have in this case is you give as input some expert demonstrations, you initialize your phi, and then what you do is the following. You first compute an optimal policy given that our phi, e.g. with something like value iteration. You compute the state visitation frequencies, you compute the gradient on the reward model, and then you update your reward model phi, and you repeat over and over again. You just, sorry about the typos. Okay, all right, and I'll just write out what that equation is here. So your derivative here would be your sum over all your trajectories inside of your data set, your features for each of those trajectories, minus the sum over the states, the probability of the state given your current parameterization. Oops. And the features for those states. So this is under a linear reward, which is what they derived it for. Okay, and so this is what you would do over and over again. All right, so let's pop up a level and check our understanding. Given all of this, what steps in the above algorithm rely on knowing the dynamics model? Is it computing the optimal policy? Is it computing the state visitation frequencies? Is it computing the gradient? or nothing required that. I told you that they did say they assumed access to the dynamics model, and I'll just write out that gradient again right here. So let's just take a second to sort of review the algorithm, check in any questions we might have about it. And all the slides are on the web, so you're welcome to go back, though I guess it might be helpful to, most of them I've just been writing out here. But you can also just think back about value iteration and how I was just starting to show that we could use dynamic programming to compute the state visitation frequencies. So remember, you probably all remember value iteration, and then this was the type of equations I was writing out. So to compute the distribution over the next time step of the states, we were doing things like summing over the distribution for the previous time step, as well as the probability of action given a state, as well as the dynamics model. So that's the type of dynamic programming algorithm they were proposing there to be able to do this. And then you can also just think back to what we need in value iteration to be able to do this. All right, why don't you talk to a neighbor and see what you got? There's a lot of variance. All right, good. So this is a nice sort of reminder of algorithms that we've seen from long ago. So the answer in this case is 1 and 2. So to compute the optimal policy, generally with value iteration, you need to have access to both the reward model and the dynamics model. So this one is true. This is true. And then the dynamics programming algorithm we looked at also required access to the dynamics model in order to kind of back up and say, if you're in this state now, what's the distribution over states you're going to be in the next time step? Once you have those, you don't need this for the gradient. So I'm just bringing that up there. Once you have all the state, once you've computed all the frequencies and you have this, you don't need it again. So assuming that you've done these two things, you don't need it again for the gradient. But it is being heavily used. And as you might imagine, that's also a pretty strong assumption. So do we actually know what the dynamics is? The dynamics model is for, say, a human physician making decisions or a surgeon. It seems quite unlikely. You might know it for Mujoko or something, but probably not in general. Okay. So let me just summarize where these things are. This approach has been incredibly influential. As we said, the initial one used linear rewards and it assumed the dynamics model is known. But there was a lot of follow-up work to this, including some really nice work by Chelsea Finn, who is faculty here now and have been for a while, but as part of her PhD, she showed that you could use general reward and cost functions, like things like deep neural networks and others. So you could use much more complicated functions and state spaces where you're not going to be able to use dynamic programming to be able to enumerate sort of the distribution over states. And then also she removed the need to know the dynamics model. So they had a really nice paper in 2016 showing how to do this with really sort of very general, rich, complex state spaces, which has also been highly influential. But I think this idea of saying like how, at a high level, the challenge was, what do we do about the fact that there are many reward models that are compatible with people's behavior? One thing you could do is you say, well, the one we're going to learn is the one that has maximum entropy. And this provides sort of a recipe or an approach to trying to tackle that problem. And it turns out that can be very effective in many cases. And in Brian Zebart's approach, they ended up using it for trying to model sort of taxi car drivers, etc. But it's been used in many cases since. So let's pop up a level. We're finishing sort of our introduction to imitation learning. What we've seen is that imitation learning is this nice approach where if you have access to existing demonstrations, and it might be hard to write down the reward function, you could try to learn from those what optimal behavior is to try to match the behavior you have access to. In some cases, it can greatly reduce the amount of data needed to learn a good policy. We haven't talked a lot about that precisely, but there's some really nice work on the theory of imitation learning in RL and thinking about some ideas we'll see later in this course around sample complexity of like, is it provably harder to learn from optimal demonstrations versus in the RL setting? So there's a lot of really nice aspects for imitation learning. The things that I think you should know in terms of going forward is you should certainly be very familiar with behavior cloning because it is a technique that is used very frequently. So you can just reduce RL to supervised learning when you have demonstrations. But it's also good to understand what this principle of maximum entropy is doing, how that relates to distribution over trajectories, and how that is then sort of formed into a maximum likelihood optimization problem to learn the reward model. Okay. And I think one thing to notice in this case is like, when they did this, they are not claiming that that is actually the reward model used by people. It is the reward model that is compatible with people's demonstrations that maximizes and a distribution that maximizes entropy. So it is not necessarily claiming that it is exactly mapping human preferences. Awesome. So now we're going to get into, this is one example of human feedback or human input to trying to use that to make good sequences of decisions under uncertainty. But there's actually a huge number of different ways to do this. And so now we're going to, this class and next class, we're going to talk some about sort of human feedback and reinforcement learning from human preferences. And I think you can think about this from many different levels. You can think about it in terms of how could humans actively try to help reinforcement learning agents that they are saying trained to do something. Like maybe they want to train the robot how to clean up their counter in their kitchen, and they have a particular way they want to do it. And so they might be actively trying to help an agent do a particular task. Or we might be just trying to align, say, large language models with our values or intents. And so then could we sort of provide information that's going to shape their behavior across many tasks? Okay. So it is relevant to both of these different types of objectives. And I'm going to go through sort of some different ways that people could be using human input in terms of these sort of training. So one thing to note is that people have been thinking about this for quite a long time. I like this work by Andrea Tomaz and Cynthia Brazil from MIT. And they had this thing, it looks pretty primitive now, but this thing called Sophie's Kitchen. And the idea in this case is that you would be trying to teach an autonomous agent how to do, like make a recipe or do some basic different tasks in the kitchen. And of course, as you can see with this, we've come a long way in the last 20 years, which is wonderful. But this kind of key insight here was, well, maybe we could learn much faster if you have a human, like instead of having an agent that's sort of trying out things like epsilon greedy and sort of exploring in the world by itself. That's not how humans do it most of the time. Most of the time we have things like schools or guardians or friends that are giving us lots of feedback and help when we're trying to learn tasks. And so their insight was to say, well, let's try to do more effective and efficient robot learning by leveraging the fact that you could have a human in the loop that's sort of providing feedback to the robot. And in this case, I think one thing that's important to note is that the robot is getting two different forms of input that they're trying to maximize. They're both getting input from the human and they're getting input from the environment. So for example, I don't remember if this exactly was in that particular domain, but you could imagine something like maybe there's intrinsic reward if you drop something, like a big cost, but then maybe the human also says, that's good when like, you know, you make the right recipe. So there's two forms of signals that are being used to train. So this is an example where it's more like Dagger. You have a human in the loop and like they are trying actively to help the robot all the time. Another version of this is the Tamer framework from Brad Knox and Peter Stone over at UT Austin. And what they were again looking at is like, well, maybe we can train agents to do things much better, much quicker if we're willing to be in the loop. And these are all different approaches than the Dagger approach. In this approach, so what are we looking at? This was older, so this is looking at Tetris, a video game. We were trying to sort of stack blocks and clear lines. And what you could see in this case is a lot of the previous work, like sort of policy iteration, and it doesn't matter exactly what these algorithms are, but there are other sort of competitive algorithms at the time, were at game 3 getting nothing. Like they just weren't clearing any lines. But after a while, they could start to learn, you know, much better. Like they could get many more later. And what they found here is that by using human feedback, they were taking human feedback and they were learning an explicit reward model. So one thing you could imagine you could be doing is doing something like model-free RL, where like you're getting signals from the human and you're using that to update the agent's policy, but then you drop it. You're not doing any parametric modeling of the reward model. In this case, they are trying to explicitly build a reward model from the human feedback. And you could see that they could get much better performance very quickly. But, you know, just like kind of maybe the problem with Dagger, people aren't going to stay around for thousands of games. And so you may not be able to exceed performance, at least in this case, of if you allowed the agent to train for much longer. But I think this is another example of where, so this is sort of a place where they're starting to do model-based approaches, where you are actually explicitly training a reward model from human feedback. And I think it's nice to think about there being at least one sort of continuum of the type of support that humans could provide. Really probably is multidimensional, but at least one, which is you could think of if humans are willing to provide data at all to train RL agents. One might be, I'm only going to give demonstrations that I'm going to do anyway as part of my normal behavior, or maybe that I'll do once. And then in another extreme is something like this Dagger or this constant teaching, where I'm like willing to be a coach for my agent and I'm just going to sit there the whole time. And one of the things you might wonder is like, well, what's in between? This is clearly a spectrum. And one thing that a lot of people have thought about quite a bit over the last 15 years is whether preferences, pair comparisons, is that sweet spot. So the idea in this case is that you're not going to ask people to do constant teaching. You're not going to, but you are going to ask them to do a bit of work. And in particular, you're going to ask them to be able to compare different types of behaviors and which do they like better. Okay? And this is kind of in between on the level of human experts. So one of the first places this was discussed a lot was recommendation ranking systems. So Yi-Sung Yu, who's a professor now at Caltech, together with his PhD advisor Thorsten Joachims and others at Cornell, did some really nice early work on thinking of if you have recommendation ranking systems. So imagine you have two different retrieval functions and you put in some query, and this gives you this, the retrieval function A gives you this series of outputs, and retrieval function B gives you the other. And you'd like to learn, because you are Google or Bing or things like that, you'd like to learn which of these two is better. And so the idea that they came up with in this case is, well, we can ask people which one is better. And in particular, you could ask people to compare, say, maybe the first item returned or the second or the complete ranking, which one is better. And that's something that might be much easier for people to do than to specify a scalar reward function for like how good it is that like CS234 is returned to your query. Like, is that 17.3 or is that 2006 or is it minus 7 billion? Like, it seems very hard to ask humans to do that, but they probably can do the comparison and they can say, well, it seems a little bit better. So that's one area, and that was sort of one of the early areas of people thinking about how could you get feedback on recommendation systems so that we could make them better? But there are lots of other applications. And as you can see, robotics and driving is one that people have thought lots about. So this is work by Dorsa Zadig, another one of my great colleagues here. And what they were doing here is to think about if you're training a car to have different behaviors on the road, how do you get input from humans about which types of behaviors are going to be acceptable? So, for example, most of us would probably prefer the thing on the left than the thing on the right, because the thing on the left does not involve a car accident. But it is hard to write down an objective function for all the things you want to do when you're driving, including like if it's hailing, or if like a car suddenly stops in front of you, or, you know, it's pretty subtle. And so what Dorsa and her colleagues showed is that people can do this sort of preference pairs. And in fact, she and her lab here has done lots of really interesting work on thinking of which preference pairs do you show to people so that you can quickly try to get a sense of what their preferences are, to try to sort of respect this human effort aspect. So these are just sort of two of the examples of the places that people have thought about this. And of course, ChatGPT is another, and we'll see more about that in a second. So in general, pairwise comparisons might be in this sweet spot because it's often easier than writing down a reward function, and it's much less work than sort of Dagger and having to constantly, you know, say, you can imagine in recommendation systems, like what is the perfect response to this query of like, I don't know, like which courses involve this. That might be really hard for people to write down, but it's easy for them to do the comparisons. Now, how do we think about this? Well, one way we could think about sort of how do we mathematically model this is the Bradley-Terry model. And as we've seen with trying to understand modeling scalar rewards, when we start to think about having people compare preferences, often we will still be really interested in understanding sort of a latent reward model. So the idea will often be that we assume that people have some reward function in their head that maybe is hard for them to articulate. And what they can do is produce preference pairs that are compatible with that underlying reward function. Now they might be noisy, you know, a lot of us all make mistakes, we all make mistakes. And so we're not going to assume that necessarily what I say is perfectly corresponding to my latent reward function, but it's going to be noisily related to that. Okay, and so Bradley-Terry model is one of these types of models that tries to relate kind of internal preferences over items to how we might compare them. All right, so let's first start off with a simpler setting before we get to RL of K-arm bandits. We're going to see K-arm bandits shortly in the course, but for right now you don't really need to know what it is except for there's only actions. So there's no states right now, just like you have K different actions, that's all. And they all have different rewards. Okay, and what we're going to assume is that a human makes some noisy pairwise comparisons where the probability she prefers BI, so item B, compared to BJ, is like the exponential model that we saw before. Exponential models come up a lot. So it's going to be the exponential of the reward for BI divided by the exponential reward for BI plus the exponential reward for BJ. Okay. So what will be the probability that I prefer BI to BJ if actually their reward is identical to me? Like if actually I'm like, I don't mind whether I have, I don't know, like deep dish pizza versus flat. I mean, I actually do have preferences, but imagine that I don't. So what would the probability be in that case, according to this model? So my internal reward for both of them is like plus 20 because I really like pizza. So what would that be for this probability if the two items are identical? 50%, right? Yeah, so this is automatically normalized. So 50% at most. If I like one thing much more, I do like deep dish pizza a lot more. So like it's probably more like that would be say 100 versus like 10. And in that case, my probability would be more like say 0.9 or 0.95, something like that. So this is just a particular model. It is noisy. If you read if I put a link later to the reinforcement learning from human feedback paper, they make some additional assumptions of how people make preference pairs on top of this model. But this is the basic model that a lot of people have been looking at recently to understand how internal latent rewards relate to external preferences. One of the important things to note here is that this model is transitive, which means that if I want to know what this sort of probability is between I and K, so those are two particular items, I can deduce it from my probability for I to J and my probability from J to K. So you can kind of chain things. So this is a transitive probability model. Okay, so this was introduced roughly 70 years ago. It's a very popular model, and it came up early on in terms of recommendation systems and others. So another thing that's useful to think about is, okay, in this setting where I just have k different actions I can take, and I want to understand, I want to learn what the reward is for somebody for all of them. If I want to think about kind of finding a maximum one, say like what's the best arm, what is the best action, I might want to try to understand how under these different preference models, what it means for something to be good. So in the class so far, we've often talked about just maximizing the value function, and we want to find a policy that's good. Now let's just think about, if I have, k arms, which of them is best? So a condensort winner is one where for every other item, you prefer item I to all the other items. So like of all the types of pizza, if I like deep dish most, that's the condensort winner. Okay? And it doesn't mean that that those probabilities have to be, probability 1. It just has to be greater than 0.5. It means I have to beat all of the other options. And I'm bringing these up right now because there's also been sort of some later discussion of how does sort of all the recent RLHF work relate to ideas from social choice and computational economics about what are we computing? What is the sort of underlying objective we're computing, and how are we distinguishing between different sorts of responses LLMs could give us? So the second thing, so this is a pretty high bar, right? This means that there has to be one thing that beats everything else. A Copland winner is a little bit less. It just says it's the winner if it has the highest number of pairwise victories against everything else. So that doesn't mean that you have to prefer it to everything else. It just that means on average it beats the others. Okay. And a Borda winner, if an item is a Borda winner if it maximizes the expected score, where the score for item Bj is 1 if you prefer Bi to Bj, it's 0.5 if they're equal, and it's 0 otherwise. So it's sort of like this discretization of the wins and loses. And typically, algorithms for k-armed or dueling bandits, again, we'll go into what bandits are more later, what they focus on doing is trying to find this. Now, I don't necessarily need to find an item, say like a ranking system that is always better than everything else. I want to find one that on average beats everything else. And they often would construct these kind of pairwise matrices where you could think of do these different actions, beat these other actions. Okay. All right, so how would we learn these? So the question is, we have all of these noisy pairwise comparisons, and what we want to do now is to see if we can extract these underlying reward functions. Why would we want to do that? Well, once we have these underlying reward functions, we could figure out which arm is best or which action is best. And in the reinforcement learning case, we could try to optimize for that reward function. Okay. So how do we do that? What we're going to do is we're going to assume we have n tuples of the following form. We have item 1, item 2, so item I, item j, and mu. Where mu is 1 if you prefer the first thing, mu is 0 if you prefer the other thing, and it's 0.5 if you don't care. So this is just like a classification task. You just think back to your supervised learning, where you just have, it should look very much like sort of a logistic regression task. And you can maximize the likelihood with cross entropy. Okay, so we're going to map it back to sort of a standard logistic loss, where we say these are, these reward models, and in general, we're going to parameterize these as like deep neural networks or some other complicated function. It could be linear, just depends. But once we have that, then we can try to find the set of parameters that maximize the likelihood. Okay, so that's how we could fit a reward model when we are given preference pairs and observe preferences. Now you might wonder, how do we do this in RL? Because in RL we have states, we have multiple actions, we have trajectories. The idea is pretty similar in some ways to what we were seeing with max entropy, and that what we're going to do is to say, well, we have a trajectory. If we have a trajectory, we can think of there being a series of rewards. So the reward of that trajectory is just the sum. So I plug in all of those sums, and I prefer a trajectory if I can get higher reward for that trajectory than the other, according to the same model. So I essentially just map it back to as if it was kind of like a bandit. Okay, it's just now that I have like two different trajectories. And we'll see an example of this in just a minute. Okay, so what do? We now are going to ask people to compare trajectories. We'll use that, then we're going to learn our reward model. And then once we have our learned reward model, we can do PPO or something with it. So this gives us a reward model for our domain, and now we can try to optimize our policy with respect to it. Okay. So let's look at an example. So in the reinforcement learning from human feedback, more precisely called DeepRL from human preferences, this came out in 2017, and they wanted to train something to do a backflip. And what they noticed here is they needed about 900 bits of human feedback in order to learn to do this. So let's see what it looks like. All right. Okay, so what someone's going to be doing in this case, so remember they're trying to train this sort of little Mujoko-like thing to do a backflip. So what they're going to show people is they're going to show them little clips. And they're going to say, is the thing on the left doing a better job of trying to do a backflip, or is the thing on the right? And they're just getting people to click left, right, left, right, left, right, left, right. And so they're not having to say, what is the reward function for doing a backflip? They're just saying, I don't know, this one looks closer to a backflip, or better. Okay. And so what you can see here is that some of them are going to be much better at like getting close to doing a backflip, right? So some of those is actually pretty good. And what they are saying is that they only needed about 900 examples in order to train it so that it could actually learn to do a backflip, which is pretty good. Okay, particularly if you think back to sort of like deep Q learning and like the enormous amount of data and training that they're often doing for, say, trying to learn Atari, et cetera, which is literally millions. Okay. So this is really cool. This is possible to do. And this is something that you're going to be doing in your homework. So in homework 3, you're going to be doing both RLHF and DPO. I'm really excited about this assignment. This is the first time we're doing it. So you can actually see how this works. So you can see how we can actually learn from human preferences. We're not making you do the human preferences. We're going to give you a data set for how we can actually train these agents. Now, I know we're almost out of time, but I'll say just a little bit about this. I'll probably have a bit of time on Monday before we have our guest lecture, but just I want to give you at least a little taste. So this was in 2017, that paper was, and there was attention to it, but I feel like in many ways there wasn't a huge amount of work on that until much more recently. So I just want to share a couple slides from Tatsu Hashimoto's NLP class. So if we just think back, I think I showed this slide on the very first day of class. How is RLHF being used for ChatGPT? What they're doing there is they're getting demonstration data and they're doing supervised learning. This is basically what we would call behavior cloning. Then they're going to get this comparison data and train a reward model. Now, in their case, they might not just use 2. You could actually have people rank between, like, say, 4 or something like that. You can extend these models to do that. So you get labelers to do that. Then you train the reward model, and then you use PPO to actually update the large language model. Now, one thing that I think is important to note in this case is that this is all really an instance of kind of meta reinforcement learning, in the sense that what they're going to be trying to do here, unlike where we've seen, like, you want to train something to do one task, like being able to do a backflip, they're trying to learn in general a reward function that covers kind of all the tasks that people might want to do with large language models. And so it's sort of this multitask problem, right? And so when they do this, they're going to give you sort of a new prompt, like write a story about frogs. And then they will want the agent to do well on that, which is likely a task it has maybe never seen before in its data. So I think that's also another important thing to note here, is that the reward models that are being trained now are things that probably would have been considered multitask settings before, but now we're sort of lifting them and saying your task is just to do whatever humans want to do with this chat GPT in terms of answering questions. And so how do you train a reward model that will be good for any of those? So we'll continue talking about this next week. We'll talk probably either before or after the guest lecture a bit about how we actually do this, but it basically just follows exactly along the framework that we've just seen there. And I'll see you then. Thanks.